Thank you. All right. Well, right. So my name is Max Pfingsthorn. I lead a group at the OFFIS Institute for Information Technology in Oldenburg, and I would like to make a case for human input and tactile input for semantic mapping today. So we've heard a number of different geometric map representations, and this of course works in 3D as well. So something that might be a line in 2D could be a plane or something like that in 3D. And of course, dynamic environments, states might be also very important. Open closed doors, like here, about to work for opening closing doors with the PR2. But I think it really becomes interesting when we look at dynamic environment objects that we might want to reconstruct as well, track them and reconstruct them in our maps. And this is also direct link to semantic mapping, right? So this is usually kind of done on the raw data that we classify for each pixel, point, and so on, some kind of class label, or also for moving objects. Like on the right, there is also a reference from the Tesla AI Day. I'm sure you've all seen it. I thought it was quite interesting what they have planned. But for me, what is most interesting for me in terms of mapping is, can we make this map detailed enough and, let's say, expressive enough to be simulated? Right? And I think this will open up quite a number of new use cases. So in terms of what makes a good map that might be simulatable at some point, right, is of course spatial correctness, but I believe it should also be correctable interactively. This includes the methods that make it behind. Of course, should be efficient. We've already talked about a bit bandwidth requirements and stuff like that. But I think the main point is that it has to be action oriented, right? So we have to be able to embed task oriented data. Has to be suitable for planning, and in general, to allow something like manipulator based applications, and which are, let's say, not the usual pick and place, but for example our work on nursing care robotics. We really need to be able to use this as a cognitive kind of work model to be able to specify tasks and then to learn action to solve this task. And I believe for that, we need to look at this, let's say, graphical model. Looking at reality, of course, we want in our SLAM problem kind of reconstruct kind of a latent environment model, right? But it's the same model that we need to make a good simulation to then be able to transfer back, right, to the real application. So I believe we then need to bring these two, reality and simulation, closer by making the link to the latent environment model that we share even stronger. And of course, this becomes our map. And then if we have a good map, which is so good that we can make a simulation out of it, we can also phrase task models and goals within this map framework, usually by programming. So, very, very simple. The simplest task model and goal would be something like a target or goal pose, where some planner might plan our robot to, but it might, of course, be much more complicated, right? Stacking boxes, kind of go to goal. type for reinforcement learning or um, assembling some assembly, right, for manufacturing. So one of the kind of go-to diagrams I always like to use is kind of this triangle, because, as I said, I want to make a case for human input to do this quickly and efficiently. And for that, of course, we kind of need to localize or put the robot in, the human into context in our system. So um, there are many use cases that we can kind of explain on this diagram, right? Something like learning from demonstration would be the robot observing the human interacting with the environment. Or let's say reinforcement learning would be a robot acting with the environment and the human kind of giving reward function. So we can usually say that to make a strong interface for the robot, we kind of really need to make it's kind of a 3-point problem, right? So the robot has to be, this connection between human and robot has to be strong, but also towards this shared environment. And for that, we like to use augmented reality. So in a way, when we visualize paths here, for example, to make it more easy for the user to understand what the robot will do next, for example, to avoid it, right? So if we know where the robot will plan to, what the trajectory will be, we can actively avoid a collision instead of kind of after the fact, right, with the usual collaborative robotics. And also visualize state and really try to use the spatial information that's kind of collected by the robot, but also something like object annotations and so on as a visual vocabulary, right, to enhance this interaction. I won't go into too much detail, but we had some nice studies to look at what kind of visualization might be good for such a path visualization. And we built a demonstrator for Hannover Fair to commission orders of Rittersport chocolate for the visitors. It was very popular. But here we also had this kind of visualization of the state of the whole machine. And this, for me, is an application of SLAM, right? To be able to have this data co-localized between augmented reality headset and the robot, and be able to show it. Now, moving on to the task model, this is quite a bit earlier work where we were able to input kind of construction task in VR. So the user could place little blocks, right? Then we would plan with the robot to do the pick and place actions to build this. But the main thing was that, of course, the dimensionality, right, of this task is very high. So you can place blocks anywhere, pretty much. You can stack them, and you can choose the color and so on. So this kind of was a toy problem for us to explore what we can do with an intuitive task model interface to instruct robots, right? And I believe this should be even better when we use our maps for this, right? So if you imagine not a plain table to be visualized in virtual reality, but a map, and then you can interact with it and say, this object should be here, or maybe, I want coffee in this mark, right? And then there be coffee in this mark, let's say, right? You can maybe say, and then robot does the task planning and so on. learns how to do the different steps in simulation and should do it. So I think this is a very, very powerful way to instruct a robot. And one of our metrics kind of for usability is if kids or politicians can use it. So this is something that we showed at Hannover Fair in 2018. And yes, both, and anecdotally of course, could use this system in a way that, of course, they had never programmed a robot before, but could still make it do within the task constraints, of course, what they wanted to do. So this was quite empowering. And we're currently then extending this towards the industrial use case for spraying release agents aluminum die casting with colleagues from Fraunhofer IFAM. And here we're basically looking at interacting with the task model for spraying on these die-cast forms, and then having the robot or the planner basically tell the robot what to do, how to achieve this goal of applying the spray. Now, looking at this difference between or perceived kind of interaction between reality and simulation again, of course, there are many works trying to go into this area, and most of all, I think it goes from simulation to reality, with sim to real transfer and synthetic data from simulation, for example, for learning tasks. But this bottom problem here, data-driven simulation worlds, is it's kind of new and has found, I think, a lot of application for learning, for reinforcement learning for mobile robots as well. And there have been some efforts to do this. For example, the Facebook AI habitat, which is scans of a real apartment, and then they had lots of manual labor, I think, went into finally making this simulation world out of it. But I think this goes into the absolutely right direction, right? So we want to have realistic data, and what we actually want, I think, is data from the specific environment that the specific robot that we're working on will move in, right, and act within. So I think the main challenges here are um, to estimate extra visual object properties, so weight, friction, and so on, to be able to do the simulation. But also, again, transfer human knowledge in terms of the goals that need to be achieved, but also, and I'll get into that in a little bit, task-specific variants that we might have to be robust against, right? We have had some previous work on extra visual object properties here as a way to gain data-driven knowledge about objects. So the robot could kind of prod the objects, right? Make them slide off a surface and so on to find out more about friction, elasticity, weight, and so on. That might be important for the use of this object, right? For example, I think the main point, really keeping back segmentation, so no, semantic slam, but also in general object recognition and so on, is targeted data from the application domain. Right? This is why everybody uses simulation to synthesize their data. But the main thing is, of course, that in traditional object recognition, we would like to then apply a label to a specific point or an object geometry, right? So in this work, we try to kind of go away from that, right? To not have to use labels, but rather use these extra visual and also visual properties to be able to match a specific object right now within the robot workspace to prototypes of, in this case, tools, something like, the question might be, I need a hammer, something like that. What object in my environment is most like a hammer, right? To be able to use it as a hammer. And through the symbolic knowledge, then it should also be, of course, localized, right? So we know which object where has what of these properties. We can do kind of label-free object recognition, which I think is also quite powerful. And in terms with the previous talks, can also be autonomously kind of explored, right? So if at some point, a Tesla bot is real, we just turn him on Christmas, as we've heard before, and it goes through all our things. On second point, maybe not a great idea, but let's say it's kind of the it just works idea that within the workspace of the robot, we should be able to not actually expend any human energy to label things, right? It should just work. And I think this is quite important. And we have recently extended this. This is not yet published. To do this quite autonomously in our model kitchen. So we have in this case here, we have a robot that recognizes this ball and then picks it up to weigh it, right, with the internal force torque sensors. So we can do this for all our extra visual properties, push it kind of across the surface to measure friction in a way, right? And then really try to explore an object and then find out these things. And I think manipulations anyway is very, very important as an additional sense, in a way, an active sense, right? To disambiguate maybe between objects, right? So if we're not completely sure in segmentation, if it's one object or two, we can try to push and then see what moved, right? To see what might be connected or not. So I think this is also very, very important for having this action and goal-oriented and task-oriented world representation, right? Which I think, again, is all part of SLAM in the bigger sense. Now, if we want to learn from a simulation, I'm sure you've all seen this. Something that people do a lot is domain randomization. And sometimes I have a feeling this is kind of made up variance, right? So this is variance that doesn't necessarily happen in real life. Of course, the real world should just look like another simulation, as Peter Abiel usually says. But I wonder if maybe task condition variance, again, input by a person, could be more useful, right? And this is actually something that we're looking at in just recently started research projects in my group. We started just this month. And yeah, so I hope there will be many cool results to be able to share with you soon. But this is basically the idea, right? To have really task specific and conditioned variants that we put in with the human interface, VR interface, to not have to learn so much variance, because the more variance it feels like, the longer this learning task will take, right? Another thing that we're addressing, of course, in the same area is domain shift. So if we have a simulation that is built on the actual environment that this robot will act in later, of course, we hope to minimize this domain shift. And of course, leveraging these extra visual properties will help. And finally, we we would then use this VR interface um, to maybe correct the data. I'm not sure yet, but definitely input this task condition. And in the end, this is something like the pipeline that we will address in the project. The first part on the top left being the semantic mapping and extraction of these extra visual object properties. And we have this knowledge transfer from the person to the system in terms of task, goals, variants, and so on that we need to take care of. And then the last part would be this task-specific domain randomization, and then, of course, this transfer back to the real world. So I think there are many potentials for human knowledge as a kind of data source, right, for SLAM, or let's say in a more broader sense, a cognitive word model. And this being, of course, two parts. One being information transfer from robot to the user in terms of just the augmented reality application that I showed before, to really try to share this kind of spatial vocabulary and interact with that rather than code, right? And also use this vocabulary to then instruct the robots in terms of these task models. And of course, to be able to learn action to solve these task models, we need to do this simulation. And there we have the need for a very extended list of properties for our map, right? Including objects, like completely 3D reconstructed objects, and of course the manipulation that we might need to do to be able to acquire this extra visual data would then also lead to changes in the scene that would help in the complete 3D reconstruction. Okay. So thanks for the team, of course, my research group and external collaborators. And I'm happy to have questions from you.
Thank you very much for the presentation. And as always, if you have any questions, please write them in the chat, but please set it to everyone. Okay, I think that I will start then. So you are presenting this, like, I'm thinking about the map in the, oh, there is also, so Jan is will be after me. So I have this this idea about the map as something very lightweight. That should be something very lightweight. And when we are describing this very complex representation, the first thing that is coming to my mind, oh my goodness, that will be very heavy to handle that. Like, am I wrong? It means like, where is or it, like, I have my biases, so I'm not sure if I'm wrong, but is it like something that is very heavy and complex, or is it like really nice and lightweight that can be handled?
So for me, it doesn't really sound a lot of, so it doesn't sound very much more complex than kind of state-of-the-art semantic SLAM anyways does, and I'm pretty sure Luca will tell us more about that later. I think it's just a lot of smaller SLAM problems kind of combined into one, right? Because what makes it a bit more complex is, of course, the kind of bookkeeping, object tracking, and so on that you might need to be able to map then locally in object space and 3D reconstruct them. But I'm hoping that this will kind of be a side effect of the dynamic, let's say, motion that is kind of introduced by poking the object, pushing it around and so on, picking up, replacing it again to weigh it. And then there will be kind of some emergent motion anyways in the scene, right? To be able to do this. And in the end, it's just so that these extra visual properties are just maybe, if you think about feature vectors, otherwise it's very, very small feature vector, right? But quite informative because like a weight is just one float. Right?
Yes. Yes.
And maybe we have some more about elasticity or something like that. But it's really, really small data.
Okay. Okay, I'm convinced. Thank you very much. So now, Jan, you are in spotlight now.
Mm-hmm. Right. So I think this comes to mind a lot for us as well because we have some projects in nursing care robotics, and there, of course, we have a very, very difficult object to object is a bit demeaning, but to manipulate, which is the patient, right? So of course, it's not only clothes that are very complex, but also more articulated legs and so on, right? But usually these are very, very localized, right? So I think this complexity should be very, very localized. So I think it's maybe counterintuitive to think of a map of maybe 2 by 1.5 meters, right? But I think that's probably what we will end up doing because you're completely right. This makes it much more complex, but I think it's kind of set off by the locality, right? Mhm. Yeah, but true, true. Yes, but also in terms of the workspace of the robot, right? It doesn't really make sense to model anything outside the workspace of the robot, because can't manipulate it anyways. So that's what I meant by locality, that you have kind of, even if it's a very highly complex object, you won't have very many of them in the immediate surrounding, right? So that's why I think it's still manageable. Also, especially with the kind of computational resources that we can carry around with a robot that can, lift the leg, for example.
Thank you very much. And now we also have Magnus to ask a question.
Yeah, thanks for the presentation. That was interesting. I was curious about something in the beginning where you had this visualization of what the robot was going to do to make it easier and safer for users. You said that it was frustrating to see the path visualization. I'm curious, what did people think about that, or why is it frustrating?
Right. That was here, right?
Yeah, the left part there.
That was part of the user study. So we had questionnaire at the end, and part of the task load index, kind of a workload instrument, is frustration. And so here in this study, the task was to solve these math problems on the touchscreen, right? So kind of to distract the participants. And then through the visualization, the participants should kind of predict when the robot would cross their space, right? To be able to take a step back and avoid the collision. And because this path visualization only shows the path of the end effector, not the complete robot kinematic chain, this was harder to perceive and kind of led to somewhat higher frustration ratings in this questionnaire, because I think because it was not very easy to understand, and then anyways people were looking at the robot more than the visualization, so that didn't quite work, right? But I think this is kind of an artifact of the questionnaire.
Yeah. Okay, thanks.